Perfect. Screen. Start. Submit. All right. So, okay. We're doing this question. We didn't get to do this question last time, so I'm gonna finish it today. This is related to somebody's question, I believe, in the group chat, if I'm not mistaken. But I'll answer this question first, and then we'll answer the person's question that was in the group chat. I'm not sure if somebody got that explanation already, but all right. So this is basically the concept of anti-periplanar having an E2 reaction, and then basically having to pull off a hydrogen from the opposite side of the leaving group, right? Here we have a small base, just so you know that we're asking for major product in this question. Although you know that dairy substrates can also undergo SN2 reactions, correct? So there's multiple products here, but because if I did do a SN2 reaction, we would get a methoxide here, right? And MOME group, right? Hold on. But here in this case, secondary substrates are more likely to go, this is the SN2 product, are more likely to go E2, correct? And it's an argument of like what's faster. Here, if I was to go E2, so this is the SN2 product, but if I was to go E2, I can't just pull off a hydrogen from the left side from the top carbon, because first of all, this is a cyclic structure. You can't necessarily twist it, right, without breaking the ring. So we can't simply just twist so we can get an oppositely sided hydrogen. But what we can do is pull from the opposite carbon, not the opposite carbon, the adjacent carbon on the right, correct? Although this would seem, instead of being like the Zaitsev alkene, this looks like the Hoffman alkene, but it's the Hoffman alkene because that other hydrogen, the hydrogen here, it's not anti-periplanar, right? Here, on the other hand, the CH2 group has two hydrogens, either of which may be opposite to the bromine, to the leaving group, right? So if we're using methoxide to pull this hydrogen off, we're going to form what looks to be like the Hoffman alkene, but it's the only alkene that's possible besides like an SN2 product, okay? And this is the first product. That's the first product, all right? This is the first product, okay? Now, OSO4 and sodium sulfite, I believe. What happens here? You're gonna have a reaction sheet, but you have to know, besides being able to read off the reaction sheet, how this works, how are you going to draw this, and if whether there is one product or two products. Usually what it will show you and what we'll expect you to put on the exam is at least one product plus its enantiomer. If it has an enantiomer, if it's the same product, well, that doesn't matter. Or if there's just one product but two of them, like in a ozonolysis question, well, then that's fine as well. Here, what does OSO4 with NaHSO3 do? What does this reagent do? Does anybody remember? Can anybody answer that question? Are we adding, what do we call these kind of acids? No? Not sure? It's chapter 8. Alkene reactions. If you don't know, it's fine. It's essentially a diol molecule. You're adding two OHs syn, or on the same side, or same side. Okay, so I'm not going to show you the mechanism. It's probably not important for this class, but you'll add those two oxygens, or hydroxyls rather, on the same side. Is this the only product? Could I have added this a different way, is basically my question. If you don't recall, this could have equally added either from on top, above the alkene, or below the alkene. So I could have drawn this equally. I could have drawn this product, where both of those hydroxyl groups are dashed. Okay. Sometimes you could just easily abbreviate by putting an enantiomer. But this technically wouldn't be its enantiomer, it would be its diastereomer, because this configuration is staying the same. So that's just a quick point. But usually with these kind of questions, you can just put plus enantiomer. Okay? Any questions so far?
Yeah, I have a question. Why is the double one added there? Couldn't it
Okay.
be? Yeah.
So you can't pull off this hydrogen that I'm pointing at. Why?
Because it's a dash?
Yes, and the leaving group is dash, right? And we have to have the leaving group and the hydrogen that we're pulling from be opposite to each other. Remember? It was the concept of anti-periplanar, right? We have to pull off a hydrogen that is opposite to each other.
Okay, thank you.
You're welcome. All right. So, all right, real quick. O3-DMS. Do we remember what this does? Do we remember where this is from? No, maybe
Is it
so.
ketones and aldehydes?
So yes, it essentially splits things in the middle, right? But how would we, like, I'm trying to think, like, how would we split this, right? This is a little bit of a tricky question, right? Because we're supposed to make either an aldehyde or a ketone, right? And let me just make sure that I think I have a second question like this. Yeah, okay. Let's see, what would be easier to explain? You basically just cut that in half, and I'll start with the first one, and then we'll move on to the second one, just because the first one is a little bit easier. But okay, so simply just cutting in half, right? Think of where the alkene is, and if I was to cut this in half, and that's where I'm putting essentially the two products. So what I'm trying to say is, what would this product look like if I was to split this? Let me see if this makes sense. You can easily just draw it like this. Here would be one of these carbonyl products, right? And then here would be the other carbonyl product. At this point, this is a hydrogen, right? A hydrogen. And this would be here. There would be another carbonyl. This would be a hydrogen as well, correct? Let me move this just a little bit. Okay, and this goes down this way. And here there's the other carbonyl, right? Attached to the isopropyl group. Okay. But sometimes you'll see, if you get a question like this, you'll notice that these two are the same product. And so if you're asked, hold on. I don't know why this is not rotating. There we go. Okay. You see how these two are the same product, right? I could have just as easily given you this question backwards, saying, what is the reactant? And expect you to come up with the reactant in which it's split from. And instead of giving you both, I'll just write something like this and put 2 times, right? And all you have to do is basically align those two, just like we did here. I'm hitting the backspace just so you can see the thought process. You would draw them basically aligned with each other. And you would notice that this compound here is symmetrical. And because it's symmetrical, it produces 2 of the same product. Okay? And that's kind of what I'm asking in this next question. I want you to come up with the actual reactant before the ozonolysis step. And so here, this question is a little bit more difficult because you're not sure, like, where did these ketones originate from? And these ketones originated from basically the same, so they're connected, right? These 2 ketones are connected. So it must have come from one alkene, right? That we split somewhere in the middle, correct? All right, how would I go about this? If we split it in the middle and it's on the same, these 2 ketones are still connected. They're not split in half like we have in the previous example.
It's a ring?
Yes, it's a ring, exactly. And so how many carbons are on this ring?
Seven?
You would think there's 7, right? Because there's 1, 2, 3, 4, 5, 6.
Do you have
7.
2 methyl groups?
Yes, exactly. There's 2 methyl groups. So really, we're looking at basically just 5. We're discounting these 2 carbons at the very end because those are going to be the methyl groups on the ring. So it would be 1, 2, 3, 4, 5 with 2 methyl groups on the ring. And maybe we could draw this a little bit clearer. How about, let's see, if I drew this maybe almost like a cyclic form, almost like a 5-carbon pentane, right? So this would be 1. Just draw like that. This would be 2. So that's 1. This is 2. This would be 3. Something like this, maybe up to here. This would be 4. And maybe up here. This is where we're getting to basically 5. And maybe I can push this down a little. Boom. And that's where the other ketone is located. So it'd be 1, 2, 3, 4, 5. And that's why I mentioned that these 2 last carbons are those methyl groups. You see? And so if we were to connect this, originally that's where that alkene basically split. So let's draw that. Basically, we're just drawing this molecule. So that cyclic pentene ring. So we see 1, 2, 3, 4, 5, and those 2 methyl groups. That's where this compound is coming from. Is that clear to everybody? So whenever you're at, hold on.
Sorry, I have a quick question.
Sure.
So when we come across a question like this where we have to come up with the reactant, we should just assume, if we're given a product similar to this, we should assume that the reactant will be cyclic.
If you have just one product, in this case, we only have one product cleavage, that's when you assume it's cyclic. If you have two products after cleavage, then you know that this is coming from something that wasn't connected and had two alkenes. Does that kind of make sense to you? So like if I had, I don't know, let's say if I had something where it's cyclic, yes, but for example, I don't know, if I had something like this, where I had two alkenes on the same product. This is a diene, right? And this diene now is going to split into basically actually two same products and four different products. I mean, depends on how you want to look at it. If I split it here, I'm forming a carbonyl. This location, but here I'm forming the same formaldehyde product here. And all I'm doing is making that same ketone on the bottom carbon, right? And so here, if I showed you like, oh, this formed this product after ozonolysis plus two aldehyde molecules, it's pretty clear that these two were first alkenes. They are cyclic, but they aren't, like, this part isn't necessarily cyclic. Does that make sense?
Yeah, it makes sense. So if it's like more than one product, then we should assume that it's not like all of it is not.
Yeah, exactly. And most likely you'll have two alkenes, right? Because if I simply just drew basically this, for example, and or just this and this split, and guess what? This is just one alkene, right? Does that make sense?
Yeah, it does. Thank you.
You're very welcome. I forgot to do the second part of this question. Somebody asked, and I think in the chat, something similar to this. Let me just make sure I'm drawing it correctly. The question was similar to, okay, knowing, all right, if I did like a Zaitsev alkene, why is this wrong? And it was basically the same thing of, this was, hold on, yeah, this was drawn as such. So we have this undergoing an elimination reaction with CH3O minus, and then it was hydroboration, BH3 tetrahydrogen fluoride or something, THF, and peroxide with a basic source like NaOH. Okay, so here, whoever asked, I hope you're in recitation right now. If not, here's the explanation. You can't, again, pull this hydrogen off because it's anti-periplanar. It's not anti-periplanar. These two, the hydrogen and bromine, are cis to each other. So where would you pull off the hydrogen? It has to be from an adjacent carbon, okay? This carbon in pink doesn't have any hydrogens. It has only two methyl groups and connected to the ring, right? So where would we pull off that hydrogen? If anybody has already answered that question, please feel free to speak up. Where would I pull off a hydrogen if this is an E2 reaction? It's okay to get it wrong. We can't twist this compound because it's a ring, right? So where are we pulling off this hydrogen? Or are we doing something else? Is it possible to do an SN2 reaction? Not really, right? Because this is a tertiary substrate. So what, any ideas? If you're not sure, what about, is this an adjacent hydrogen? It is, right? There's actually 3 hydrogens there, correct? 1, 2, 3. And could we not, and that's an adjacent hydrogen, that, can we just pull that hydrogen off? We could, right? So if I pulled this hydrogen off, well, guess what? These electrons are now donated here to make an alkene coming off of the ring and kicking this leaving group out, right? So for that person that was asking, like, oh, wait, where is the alkene being formed? Well, now it should be obvious to you that the alkene is now being formed here in between these 2 substituents, in between the 2 dimethyls and this 1 methyl. Okay, now all you have to do is then answer this hydroboration question. And what does hydroboration do? It adds an OH to what side? The more or least substituted side?
Least.
Least. Okay, so this is the least substituted side. We also add a hydrogen. You also add a hydrogen. And they're pointing to the same side, but that's not important because you don't show the hydrogen. Boom. There's your answer. Okay. So I hope that made sense. And I hope whoever asked that question is watching or will watch the recording later. All right. So how about here? All right. Here's just a simple question of like, what if you were asked a simple synthesis question, what reagent are you using? Which reagent would be essentially faster, or which reagent would you use in such situation? In this case, you have an alkene that's external or terminal, and the other one is internal. It's in the middle. So can anybody tell me, for example, I don't know, you pick, what can you identify, what reagents would you add and where?
Can we add NaOH?
NaOH? No, we're adding, so this is an alkene. This is either hydroboration or what's the other one? Do you guys remember? It's either hydroboration or oxymercuration, demercuration, right? And it just depends on when you're using, like, which one. So whether this is adding to the most substituted side or least substituted side. And so in this case, it depends on what do you want to do. You can use OH here. Hold on. You can add OH here, right? But this would be the least substituted side, right? So least substituted side, which one is that? Is that hydroboration or oxymercuration, demercuration?
The top one.
Excuse me? Okay, so if you're adding, oh wait, go ahead.
Is it hydroboration?
Yes. So
Least.
hydroboration, yeah, adds least substituted side. So these are the most useful reagents to add OH to an alkene. What we just did in the previous question, right? Now here, this is most, correct? So out of process of elimination, you know that this would be oxymercuration, demercuration. So something that looks like this. And this is in water followed up by some kind of, this is a hydrogen source. Sodium borohydride, actually. Borohydride. Okay? So that's just a simple synthesis question. This is a one-step synthesis.
Can you
Not too bad.
Can you explain again why it is moles, like how to identify it is moles and least?
Because here, how many on this side of the alkene, how many substituents do we have? How many R groups do we have?
Oh, okay, thank you.
Yeah. And on this side, we have at least one R group. This isopropyl in here, we only have hydrogens, right? So the left side would be the most substituted side. Okay. All right. Real quick. We have a couple mechanism questions that I want to go over, and they get increasingly harder. We're gonna give you a mechanism question, so just be prepared to practice mechanisms. Here we have a simple mechanism, and essentially what looks to be happening is that we're moving that OH group from, let's say, from this carbon, let me color that in blue, to the carbon in green. How am I doing this? Not to spoil anything, but there's technically different ways to do this, but the only way you'll learn is by basically creating a good leaving group and then attacking it with a good nucleophile, right? So that's the first hint. What happens to this OH? It doesn't disappear, but it could be the same OH, or is it not? If I was to radioactively label this OH, would it be a different OH that's adding to the ring? I don't know. You tell me. What happens to this OH? What's the first step? Is it
It's proton transfer from the hydronium.
Yeah, proton transfer. You see hydronium, you think proton transfer. Okay? So that makes water a good leaving group, right? A positively charged water into a good leaving group. Okay, what's next?
Methide shift?
Yes, it is.
Or so,
No,
well, that leaves, and then there's methide shift.
yeah, first it leaves. This is proton transfer, right? Then water leaves. Leaving in its place is a secondary carbocation. And then, yes, you are right. It's a methyl shift. Methyl shift. You could have equally done a hydride shift, but a hydride shift doesn't get you closer to your product. So we do a methyl shift. This is rearrangement. Now we get an even better, more stabilized tertiary carbocation, right? And we're very close to our product. All you have to do is now, it could be the same water molecule, but because this is in solution, it's very unlikely that this is the same water molecule. So you have now a water molecule attack. This would be nucleophilic attack, right? And what's the final step, Joseph? Or anybody else that wants to talk? Excuse me?
Nucleophilic attack.
It's technically not considered a nucleophilic attack. It's considered a proton transfer because another water molecule picks this hydrogen up. Okay?
Okay.
Is it
Hydronium. Go ahead. I can't hear you. You can repeat your question, please.
Was that meaning deprotonating?
Yeah, so either pronating or depronating is considered proton transfer. Here, what's happening is that you're depronating water, right? But you're pronating this water molecule. This is being pronated. to then form hydronium, right? Because hydronium acts as a catalyst. It's neither consumed nor produced. It's just it reforms. It's just used to help this reaction move forward. Okay, and that's how we moved that OH from one side, the carbon in blue, to the carbon in green, and we had a methyl shift, basically allowing that to happen. Okay. Next mechanism. This one is a little bit more tricky. All right. What's going on? Anybody? What's happening here? Little lost? No idea? Okay, we're forming a carbonyl, or rather a ketone, right? We also formed a six-membered ring, correct? And we lost one of these hydroxyl groups. So we know that one of these hydroxyl groups has to be converted into water, a good leaving group, and it must leave. And then something else has to happen for it to form a six-membered ring. I'm breaking that ring like we did in our last class, where we had rearrangement via, a carbon-carbon bond breaking and reforming. And then we form this carbonyl group. Let's see. At least we know that we have to get rid of one of these water molecules. So what seems most likely to, which water molecule seems most likely to be lost? Is it the one in blue or is it the one in green? Blue, right? Because it's not on the ring, obviously. So this gets pronated, right? Okay. Water leaves, right? We have what do we have afterwards? So this first step was a proton transfer, PT, then water leaves, loss of a leaving group. So now this is the molecule that we're forming. OH. Hold on, let me just look better. Okay, so now we get this positively charged carbocation. Okay, we know that tertiary carbocations are stable. What's more stable than a tertiary carbocation?
Is it secondary?
No. We
Not
have
having a carbocation.
yes, but we're not gonna attack it with another water molecule because we go back to our reactant, right? So think about it this way: how can we place, how can we make a tertiary carbocation with something more stable? So we have, in terms of stability, we did this last time. Stability. What I forgot to mention, and this is true mostly with all things, is that if something has, what's the word? It starts with an R. So this is least stable, secondary, a little bit more stable, tertiary, a little bit even more stable. But if I had tertiary starts with an R, you learned about it a lot.
Rearrangement or resonance.
Rearrangement.
Resonance. This thing has resonance, or as the young people like to call it, Riz, or I don't know. It has resonance, right? That was a joke, but anyways, it has resonance. And how do we make this? I know it's a tertiary carbocation, but I want to make this more stable. And if I made this more stable, I could I would have to have a tertiary carbocation with resonance. So I would have to have a tertiary carbocation with resonance. And do you see where we can form a tertiary carbocation with resonance? There's a lone pair. On
Yeah,
this
you can bring that over.
Yeah, how would you bring that over?
It would form a pi bond with the carbon at the top of the pentene or pentane.
So, oh shit, I originally drew this wrong. It doesn't matter though. I can fix this. Because what I drew isn't what I had intended to do. These two were supposed to be on the same carbon. Geez. Okay. You could do this. All right, well, this is not going to be the same product because this is a slightly different product. We're not going to get this product. I made the wrong product when I was actually making this question, but we can still go on with the same example, because this product would have needed this hydroxyl group to be here at the carbon in pink for that to form. But that's not important. I mean, we can form our more stable product still by breaking a carbon-carbon bond and reforming it. So the bond that we're essentially breaking, which one is it? Is it this one? The one in red? Are we breaking this bond in red? And are we reforming it here? Or are we breaking, hold on. Or are we breaking the bond in green and reforming it here? You see, this is the problem because this I drew this incorrectly. So this is making this tertiary carbocation to tertiary carbocation with resonance a little bit harder because what we're forming is a secondary. Either way, we're forming a secondary. Actually, hold on. Let me see. I broke this bond from here. No, that's still, it doesn't work. Let me just adjust this question because then I can't do this example of tertiary carbocation with resonance. So let me fix this real quick. So this product or this reactant should have been here. Let me erase all this. This should have been this structure. And here, let's take this away. I'll just redraw it. There we go. So that should have been this product here. Same steps apply where we're pronating, right? And hopefully this is a little bit more clear. We have OH. We form, once this leaves, so this here, I'm gonna draw everything out again, just to not confuse you guys. This has two methyl groups. This leaves. Now we form this species, OH. Okay, now we're at the correct spot. All right. So tertiary carbocation, what's more stable is something with tertiary carbocation with resonance. So now we know that.
Can you zoom out again if you don't mind?
Yes.
Just like
This-
a little more.
This
Yeah,
OH,
that's good. Thank you.
yeah, this OH should have been placed here. Okay. That was the mistake. That OH should have been placed there. Okay. Now, all we have to do is remember this argument, right? And move that bond that's in green. That bond that is in green is going to break and is going to reform. Whoops. It's going to reform here. Okay. That's what makes our 6-carbon membered ring. Because if you look, And if I was to number this, this was originally 1, 2, 3, 4, 5. I'm breaking the bond between 1 and 5, and I'm reforming it basically between 1 and 6. Once that happens, then you're able to get these two methyl groups on the same carbon, on carbon number 6. And this forms a tertiary carbocation with resonance. This is the tertiary carbocation with resonance, because 1 no longer has 4 groups, only has 3 groups, and there was no implied hydrogens at 1. This was a 1 originally. This was carbon number 1 originally. It had 0 hydrogens here. There was no hydrogens here, right? So now it has a tertiary carbocation with resonance. And what I mean with resonance is that these lone pairs can be pushed down to form a pi bond. Once that happens, you form a carbonyl similar to in your product. You form the carbonyl. You have those 2 methyl groups, but now you have this carbonyl with a hydrogen. What's the formal charge on this oxygen?
Plus.
+1, right? +1. And what would we do here? I'm just going to create a little thought bubble here. Thought bubble. Thought bubble. Okay. How do we get rid of that positive charge? How have we been getting rid of all these positive charges?
Proton
On-
transfer, and then you can bring then you can form a pi bond.
All you have to do is a proton transfer with water.
Oh yeah, sorry, you already had it.
These 2 electrons just get donated to water or to the oxygen and give it its lone pair. It's 2 lone pairs that it always needs. It always has at least one of these lone pairs, right? But the other lone pair is being shared with hydrogen. And once those electrons are taken away, these in pink, they become these lone pairs in pink. Okay? And now we've formed our product. Okay, 1 second. Put this person in. Okay. So just to recap the steps, because it was a little wonky, one more time, and sorry for that mistake. This OH should be placed at this carbon at the end of that substituent. What happens first is that carbon number 1, this OH remains. That's what's becoming this ketone. This OH first gets pronated by hydronium. Makes it a good leaving group. Water leaves, right? Makes a tertiary carbocation, correct? These 2 methyl groups are the ones represented here. That tertiary carbocation is stable, but what's more stable is a tertiary carbocation with resonance. The bond between 1 and 5 breaks and reforms between 5 and 6. If this bond in green is newly formed, the positive charge is now next to the hydroxyl group. Why? Because originally the carbon at number 1 didn't have any implied hydrogens because it already had 4 groups. Once we have this positively charged tertiary carbocation with resonance, we pull down one of these lone pairs. This lone pair forms a carbonyl. This carbonyl still has this hydrogen attached to it. These electrons in pink reform the lone pair that it lost by forming that carbonyl. And all we have to do to reform that lone pair in pink is proton transfer by depronating this molecule with a water group, which is considered a proton transfer step. And that's how we get our final product. Questions?
It's a little bit of a lot. If you could just explain like one more time. Like I wrote it down, I'm following like what you're saying. I just get confused a little bit.
Okay, so we identified which hydroxyl group was leaving at the beginning, right? It was either this hydroxyl group or it was this hydroxyl group. This hydroxyl group stays on the ring, right? This hydroxyl group, that's how we identify that one is the one that's leaving. But we can't just kick out a hydroxyl group. We have to make it into a good leaving group, correct? So to make it into a good leaving group, we have to pronate it. Hydronium is the source of H plus, or just the source of protons. A lone pair from the hydroxyl groups picks up a hydrogen. I'm not showing it, but picks up a hydrogen here. It picks up a hydrogen, right? That hydrogen now pronates this water molecule. Water, now positively charged, is a good leaving group. It leaves, once it leaves, it forms a tertiary carbocation, right? That tertiary carbocation is stable, but what's more stable than a tertiary carbocation is a tertiary carbocation with resonance. Originally, we had this pentane ring where we had a bond between 1 and 5. And what do we have to do to form a tertiary carbocation with resonance is breaking the bond between 1 and 5 and forming a bond between 5 and 6, because that allows a positive charge to be formed at carbon number 1. Why is a positive charge formed? Why is a positive charge formed at carbon number 1? It's because originally carbon number 1 didn't have any implied hydrogens. Now that we have a tertiary carbocation with resonance, a lone pair on that hydroxyl group can push down, form that carbonyl group that you see in our product. And once that carbonyl group is formed, we notice that this hydrogen is still there. That hydrogen, which is bonded to oxygen, has these lone pairs that are the lone pairs in pink that you see that oxygen has at the very final step in its final product. What we need to do is basically depronate this pronated carbonyl with water so it can gain those lone pair that originally lost because it was forming that pi bond seen here. So this basically that pi bond that I'm forming in blue is this one right here. Okay. Is that a little bit clearer? We'll have more questions. I have like 6 more mechanisms to do.
Yeah, that was clear. Thank you.
Okay, cool. This is another one, and this is a little bit easier, but this is basically the formation of the carbonyl one more time. So let me go ahead and change to black. Okay, so here, which hydroxyl group, whoever just asked the question, which hydroxyl group is leaving? Is it the one in blue or is it the one in green?
The
Blue.
top one?
Top one, right? Good job. Because this carbonyl is the one forming. Cool.
What was the question again?
Which hydroxyl group is leaving?
Oh yeah, this is top one. Okay.
Cool. So lone pair, right? That it's pronated. Okay, boom. We're forming a good leaving group. Boop, boop. Right? This leaves. Once it leaves, I form this product. And this is a tertiary carbocation. Can anybody answer what's better than a tertiary carbocation?
Tertiary carbocation with resonance.
Okay, and now am I breaking a ring and reforming it to make a larger carbon ring? No, because it's not a ring. So what am I doing?
Can you
Methyl
repeat it again?
shift.
Methyl shift. Whoever was asking a question, basically all I'm asking is like, what am I doing to make this into a tertiary carbocation with resonance? And you're right, I'm doing a methyl shift. This methyl group, now in gray, is basically moving to this position. So now what we're forming is this OH. Okay, am I missing something? What did I do wrong? What am I missing?
You need a pi bond on the hydroxyl, the alcohol, sorry.
Right, but how did I, before I get that pi bond, what am I missing to make that pi bond?
The
What
charge.
did I miss? The charge, right? I'm missing a charge here. This is tertiary carbocation with resonance. And how do I form that carbonyl? How do I form that pi bond?
Move one of the lone pairs to form the pi bond.
So that lone pair in blue forms that pi bond, that carbonyl group. Okay, now, boom, we have,
The blue lone pairs, they form the pi bond, you said?
yes, ma'am. But now I have this hydrogen. And what's the formal charge on oxygen in this state?
+1.
Okay, and how do I get rid of that hydrogen? How do I
Proton
depronate?
transfer.
Exactly. So I would use a water. To get rid. So now electrons here being shared are now donated back to oxygen. And that forms our product. Still has that lone pair and another lone pair that it never lost. Okay? Do we feel comfortable? Now let's put all of this together. Okay, now we have a whole bunch of things going on. And let me move this down to make more space. All right. Now we have hydroxyl groups leaving. We have carbonyl formation. We have two rings. And somehow they're getting closer to each other, right? Oh, and here I made the same mistake. I made the same mistake when I made this question. This hydroxyl group is not supposed to be there. To make the tertiary carbocation resonance, this hydroxyl group is supposed to be placed here. And let's get a thicker pen. This hydroxyl group is technically here. Okay? Beautiful. What's step one? Which one am I pronating? Which one is leaving? Does it matter? Is this not the same, basically like a symmetrical compound? Like it's the same thing on either side, right? So could I not say that the blue carbon and the green carbon are the same one, right? So it doesn't matter which one leaves, but we know that one of them has to leave. For the sake of argument, let's just pronate the one in green because it's going to be easier to visualize with our product. Okay, so first step, make hydroxyl into a good leaving group. OH is still there. Now this one becomes a good leaving group, right? That, once it leaves, this leaves, you have a tertiary carbocation. And now what are we doing?
You're gonna reform the ring.
So we have to break the ring, right? We have to break the ring and then reform it somehow, right? So what I'm asking is which, like what, if you were to label this, we have to put the positive charge here, correct? So what bond would I be breaking to form that?
The one that is attached to alcohol?
Yes, correct. So we're breaking, let's say, this bond. If I was to label this 1, 2, 3, 4, 5, I'm breaking the bond between 1 and 5, correct? I'm breaking this bond between 1 and 5, and I'm reforming it here at, let's say, carbon number 6, if you will. Right? Because we have to make a 6-membered ring. 1, 2, 3, 4, 5, 6. And that 6 carbon was technically part of this pentane ring. So that's how you know that we're not breaking any carbon bonds in that pentane ring. Rather, we're breaking the ring, the pentane ring to the left, making it a hexane ring. That's why we broke the bond between 1 and 5, the bond that was originally here, and we're now forming it between 1 and 6. So let me draw that real quick. So this would be a rearrangement step, right? And let me draw this bond in blue. So that's 1, 2, 3, 4, 5, 6. But that carbon 6 is the one from the pentane ring, right? And we still have this hydroxyl group. Now that hydroxyl group, carbon number 1 originally didn't have any implied hydrogens, right? Had 0 implied hydrogens, right? There's no hydrogen there. So it must now have a positive charge. And because a tertiary carbocation with resonance is a little bit more stable than just the lone tertiary carbocation, we have made a better, more stable structure. So now that there is a lone pair on the hydroxyl group, that lone pair in pink is going to donate and form a pi bond here. That is going to make our, hold on, let me make this a little bit more to the right. That is going to form our carbonyl group. But that carbonyl group still has that hydrogen, and we remember that the positive, that formal charge is on oxygen, and all we have to do now is depronate it with water such that the electrons now in green come back to oxygen. And so you have that represented by these green electrons and the electrons that are never lost. Okay. Do we feel comfortable with mechanisms? I think that's the last mechanism that I have. Is this okay? Was this hard? Do you get it now? You have plenty of practice in the textbook and in the test banks that we gave you, or the practice test that we gave you. You will have a mechanism question. I don't know if it'll be a combination of, you know, breaking a ring, reforming a ring, moving a hydroxyl group, something like that. But just be sure to go over these examples, and you should be fine. Yeah. Where's the other mechanism question? This mechanism question. Yeah, so you'll get something like this, okay? Be sure to practice. All right. Okay, real quick, let's do some major products. So ground control to Major Tom. What am I doing? What's the first step, guys? This would be considered concentrated sulfuric acid, if anybody's wondering. Anybody? Anybody at all? Talk to me, people. I'm not the one taking the exam.
Are you gonna start with a proton transfer?
Yes, sir. So once we have a proton transfer, we're gonna get rid of that water molecule or of the hydroxyl group, right? This is essentially H2SO4 source of protons. So that becomes a good leaving group, right? That's going to leave, but we don't want to form a primary carbocation. So what's going to happen? So let's say, I mean, hypothetically, we did form that primary carbocation.
Are you gonna
Which-
move are you gonna lose a proton to the bromine?
Hydride shift?
It's not a hydride shift, but something very similar to a hydride shift.
Methyl shift?
It's a methyl shift. It's a methyl shift.
When do we know when it's going to be hydride shift and when it's going to be a methyl shift?
So you tend to always make the shift that is smaller. So in this case, the only thing available, there's no hydrogens here, right? There are no hydrogens here. The only thing available is a methyl group, correct? How would we do a hydride shift in this case? There's no hydride shift to be had. Do you see what I'm saying? You make the shift that creates the more stable cation or carbocation.
If there was no methyl on the top, would we create a hydrogen there and then shift it?
If there was a methyl here, you're saying?
If there wasn't a methyl on the top.
Here, if there wasn't a methyl here. Am I understanding you correctly? Like, let's say there wasn't a methyl at this position. Well, then yes, in this case, you would have a hydride shift because what you're creating then is now a tertiary carbocation. It's still more stable, right? But since we didn't have that hydrogen there, what was originally there was a methyl group. That's why we do a methyl shift.
Okay, thank you.
You're welcome. So now that so this methyl, the one I shifted, is this methyl group here. Okay? Yes? Good. So that methyl shift, and I'm drawing the mechanism a bit. All you have to really remember is that H2SO4 with heat, especially when you're reacting it with high hydroxyl, is going to form your Zaitsev alkene. And so the alkene that you're technically forming after the first reaction, this first product, is going to be your Zaitsev alkene. That alkene, the only place that it can form is right here, right? And it's arguable of like what happens first is like, are you pulling the hydrogen first? And yes, you would originally be pulling a hydrogen from this methyl group that was, from this methyl group that was originally the primary carbocation. So this one technically still had two hydrogens, right? And this last step would have been taking away, possibly with a water molecule. This is still all of step one. You take away this hydrogen, let's say with a water molecule. And these electrons in red form a pi bond here. And that makes your first product. This first product is the Zaitsev alkene. But all I wanted to show is that there's rearrangement with a reaction like this. This is what we call an E1 elimination reaction. And E1 elimination reactions have rearrangement. E1 always has rearrangement. Okay? This is an E1 reaction here. Okay? So what now? Okay, that's all fine and dandy. That's our first product. What happens after I basically halogenate this? I make a dihalide. What is Br2 and carbon tetrachloride? What does this do?
create two bromines from the
Yes. It adds two bromines, or just two halogens, but two bromines, yes. How do they add?
one on the wedge, one on the dash.
Yeah, opposite to each other. Opposite to each other. So on to an alkene, I'm adding a bromine here and here, right? So let's draw those. So after Br2, carbon tetrachloride, I'm adding two bromines that are opposite to each other. And I'm going to draw this like this. So let's say this is on dash and this is on wedge. Okay? So when you see H2SO4, think Zaitsev alkene, think E1, think rearrangement. And when you see Br2 carbon tetrachloride, simply think adds two BRs opposite to each other. Cool? Not too bad, right? All right, here we have a very similar example. It's almost as if we had the same substrate. But here we have a tertiary alkyl halide. This carbon in green is a tertiary substrate. And I'm using, what kind of base is this? Anybody? What kind of base is that?
Is it a bulky base?
Yes, sir. It is a bulky base. This represents three methyl groups, right? Here are the three methyl groups. That's CH3 times 3. This is the carbon that it's referring to. That carbon, let me draw it with a color. This carbon in green is this carbon, right? It's connected to an oxygen, right? And usually you have some kind of spectator ion, like Na+, or you learned in class, usually I'm sure Eric drew it like this, OK, right? Terp butoxide. This terp butoxide, it's technically considered or called potassium terp butoxide because this K is a spectator ion, represents K+, and this, it's a O-. But you could draw it like this with the K+ or any other, you know, alkali metal, any like, you know, group 1 metal. But you most likely may see it like this, or we'll probably just write it as terp butoxide or TBuO-. Quote, just to look out for that. I think we're just gonna write it like this. But if we did decided to write it like this, and in the practice exams, that's how they write it. So just know that that's terp butoxide. Okay, this is a bulky base, right? What is it going? Is it going SN1? Is it going SN2? Is it going E1? Is it going E2? What is this? SN1, SN2, E1, E2? Is this a substitution reaction? Did you ever see bulky bases giving a substitution product? No, right?
Is it E2?
It is E2. Okay. So if it's E2, where am I pulling a hydrogen from? Am I pulling the hydrogen from here? Am I pulling the hydrogen from this carbon or this carbon? So here are your options. 1, 2, 3. Where am I pulling the hydrogen from? Which carbon? Carbon number 1, 2, or 3? And whoever just spoke, you said E2. Is there rearrangement with E2 reactions? No, right? Because it's concerted. And we have to pull a hydrogen that's anti-periplanar in E2 reactions or E2 elimination reactions. If I pulled Okay, let me just draw the possible products. Like, because 1 and 3, since it's symmetrical, are the same alkene. You answer this question, and rather, I'm going to, instead of number these, I'm going to letter these as A, B, and C. If I pulled a hydrogen from carbon number A, or carbon A, I get this alkene. If I pulled it from carbon letter B, I get this alkene. And if I pulled it from carbon number C, I get this alkene. A, B, and C. What's the right answer, guys?
C, A, or C?
No. Why is A and C, which by the way are the same alkene, why is that wrong? What kind of alkene is this? Is this Zaitsev or Hoffman?
It's a bulky base, so it should be.
Hoffman? Is it Hoffman?
No, this alkene here is not Hoffman, because what is the definition of Hoffman? It's the least substituted alkene. So here it has 1, 2, 3 substituents, right? Same thing here. 1, 2, 3 substituents. So this would be considered the Zaitsev alkene. Both of these are considered the Zaitsev alkene. The choice B here is the Hoffman alkene. This is the Hoffman alkene. And like somebody was saying, E2 bulky base makes the Hoffman alkene. Okay, so B is the correct answer. But that's just the first product. That's just the first product. Okay, so after creating the Hoffman alkene, we hit it with HBr and peroxide. Peroxides make radicals, and you don't understand radical chemistry because you have yet to see chapter 10. You won't probably, Eric may not review all of the important intricacies in radical chemistry or the mechanism for HBr and peroxide, HBr and ROR, but you should know one simple thing. If I use HBr and ROR, am I adding, like, what does this do? Does anybody know? What does HBr and ROR do?
It destroys the double bond and then bonds the Br to it.
Yeah, so it adds Br, okay? We've established that. But where does it add? Does it add to the carbon in pink, or does it add to the carbon in green?
The carbon in pink.
Does everybody agree with him? Does anybody have a different answer? Do we think that it adds? So you're saying if this was, you're saying it adds like this, right? Is that correct?
Yeah.
No, that's not correct, because HBr and ROR adds Br to the least substituted side. It's anti-Markovnikov. And remember, anti-Markovnikov adds Br to the least substituted side. Do we remember this? So if it was just HBr, if this was just HBr, you would be correct. This would be our product. But since this is HBr and peroxide, it adds to the least substituted side. Okay? So our final product looks like this. Okay? So to sum up, we have a bulky base. Bulky bases are going to go E2. And the kind of alkene that it's going to make is the Hoffman alkene. And we determined that this was the Hoffman alkene because we noticed here it had 3 substituents on the alkene. Here it only has 2. And A and C are the same answer because this compound is symmetrical. And now, after we got our first product, which was the Hoffman alkene, we treated it with HBr and peroxide. HBr and peroxide adds a bromine and technically a hydrogen, but it adds a bromine to the least substituted side. This is an anti-Markovnikov addition. And we just re-emphasize the point. If this alkene was treated with just regular HBr, it would add Br to the most substituted side, which would be the side in pink, the carbon in pink. But since it's HBr and peroxide, it adds to the green carbon, and that's where it would add, okay? So that's our final product here. Cool. All right, now, since we've already determined that HBr adds to the most substituted side, let's answer this question. Here in this question, can anybody tell me, first of all, answer me this question. Does it matter? Well, all right, HBr is going to add to the most substituted side, right? But in this case, this doesn't go necessarily as a regular Markovnikov addition. This is an SN1 reaction. SN1 has rearrangement. And Br isn't just going to simply add to one of these carbons. First, we're going to, since this is an alkene, what's going to happen? This is a very interesting question. Answer me this. If I add, since this is an alkene, picks up one of these hydrogens, right? Does it matter where I'm adding this hydrogen? Am I adding this hydrogen in blue or am I adding this hydrogen in green?
Either one.
Either one. Why?
It's symmetrical.
Right. So if it's symmetrical, guess what? Let's say I added it to the one in blue. Okay. So that one in blue picked up that hydrogen. Okay. Now we have a positive charge on the other side of the alkene. Since this is an SN1 reaction, Br just doesn't simply attack that secondary carbocation position, right? Because we can technically form a more stable carbocation. Since this is secondary, this is a secondary carbocation, can we not form a more stable carbocation by just somehow moving this positive charge to a tertiary position? And for the person who was asking, when do I move either a methyl shift or a hydride shift? Well, here's your answer. We have a group, and technically we have both groups. We have an implied hydrogen here, correct? There's an implied hydrogen here. If I moved, so let me say this one more time. When do I move a hydrogen? When do I make a hydride shift or a methyl shift? So when hydride shift, when do I hydride shift, and when do I methyl shift? Methyl shift. Okay. And basically I told you whatever makes more stable carbocation. If I decided to move that methyl in green, well, guess what? If I did a methyl shift here, which is the wrong answer, if I moved a methyl, I made this methyl group move, then guess what? Where is my positive charge? It's now secondary. Is that making it any more stable? It's not making it more stable, right? That's how you know that this is not a methyl shift. This is a hydride shift. So instead, I'm moving the hydrogen. So let's keep the methyl where it was. And I'm moving the hydrogen. The hydrogen is the one moving. Okay. So since we had a hydride shift, since we had a hydride shift. So this is where that hydrogen is now placed. I formed a tertiary carbocation. Now that Br anion, this one, now that attacks here. Okay. Now that Br has attacked that tertiary carbocation position, we have something that looks like this. Cool. What's next? What is this? We just talked about it.
Bulky base.
Bulky base. And what do bulky bases produce?
Hoffman.
Hoffman, correct. So bulky bases produce a Hoffman alkene. Where am I pulling the hydrogen from? Am I pulling it from here? Am I pulling it from here? Am I pulling it from here? I can't pull it from here technically because that's not, and well, technically I could, but that wouldn't make my Hoffman alkene, would it?
No, you could do either one of the top or the right one though, right?
Right, because they're the same thing. It's not a chiral molecule, and they're both adjacent. So either I could have made this alkene, or I technically could have made this alkene. But guess what? These two are equivalent to each other. They're the same compound. I'm just rotating essentially that sigma bond. It's the same thing. And so after bulky base, after I treated this with a bulky base, I formed my Hoffman alkene. Okay. So the point with this question is determining, okay, when do I hydride shift and when do I methyl shift? I hydride shift because I made the more stable carbocation, which allowed Br, our anion, to attack here. It attached. Once it attached, we treated it with a bulky base. We're going to pull off a hydrogen from an adjacent carbon. That adjacent carbon is either this one, or this one. But this hydrogen, if we pulled off this hydrogen in E2 elimination product, would give us a Zaitsev alkene here. We don't want the Zaitsev alkene. We want the Hoffman alkene. So we either pull from here or here, but we notice that these things are symmetrical. And so it doesn't matter because it produces the same alkene. Okay? Questions? Questions so far? No, maybe so. Easy. This is going to be cake for me. No? All right. Well, now we're going to move on to a little bit of synthesis. And really, there's just like 2 more questions left. And I think you guys will have covered every single topic that's going to be on the exam. I have a simple, easy synthesis. This is as easy as your synthesis question will get. You won't have more than 3 or 4 steps, maybe 5. It just depends. But you have to understand how to do a synthesis question. And you can do this either going forwards or going backwards. So retrosynthesis or retrosynthesis analysis is a whole course in organic chemistry and just in chemistry in general. You have not built up your tool belt enough to do this in the forward process. So most teachers, most professors teach this in backwards. I personally like going forward because I can visualize it a little bit better. But they tell you to go backwards. And if I want to go backwards, well, okay, cool, that's fine. But what it's basically asking you, if this was my product, this is my product, what reactant am I using? What reactant am I using? And what reagent am I using to get to my product? And since you've only discussed chapter 7 and chapter 8, well, this is actually quite simple because there's not that many. And so here I'm going to tell you basically it's the same thing that Eric told you. How do you make an alkene? You make an alkene usually from an alkyl halide. Technically, you can make an alkene from a hydroxyl group with an E1 elimination reaction, but that's a little bit harder. It's easier to remember that you make an alkene from an alkyl halide, some alkane with a halogen. Okay, so I make an alkene from an alkyl halide. I can make an alkyl halide from an alkene. That's the thing. So I make an alkene from an alkyl halide. Where or how am I going to make an alkyl halide that is going to get us closer to our product or to our reactant? Sorry, this is our reactant. Okay, so how am I moving this double bond to a terminal position? Because notice it's just an alkene, right? It's just a simple alkene that we're basically moving from our like Zaitsev position or our most stable position to our like Hoffman position. How am I moving that alkene? You've only learned a handful of reactions. So we know that if we're going to move that alkene, somehow we will have had a good leaving group, a halogen, right? Okay, cool. All right, where am I going to place a halogen? Is it going to be on top here? Let's say the carbon in green, or is that halogen? Will that halogen have been placed on bottom, carbon in red? Where's that halogen coming from? Are you guys lost? No idea? Do you see it? Do you not see it? Do you smell the chemistry? If it's
I don't
easier,
smell it.
you don't smell it. Okay. If it's easier, think about this going forward. If I did a couple of reactions to go forward, you know, I will have essentially had to saturate this alkene, place something here or here, and then maybe get something here, and then so something would technically have been placed here, and then make an alkene here, right? Or there may have been some rearrangement. But okay, so let me just write some things out. How do you make an alkene? How to alkene. And you should know alkenes can be made from alkyl halides. Basically, an alkane with a leaving group, or rather a halogen, because halogens are good leaving groups. And how do you make an alkyl halide? Well, from an alkene. That's the thought process. Dot bubble, dot bubble. So boop, 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 boop. How do you make an alkene? From an alkyl halide. Okay, so that alkyl halide will have a halogen either here or here. Let's look at our reactant. Where is it more likely to have placed? Where is that halogen being placed? Is it being placed in green or is it being placed in red? Think.
Is it green?
Okay, if it was green, that means that originally it looked something like this, right? And we treated this, let's say, with a small base, like, I don't know, methoxide, right? A small base like methoxide, technically, mess this up. A small base like methoxide. That would make a Zaitsev alkene. This is a Zaitsev alkene. All right, but look at our reactant. How does this get us closer to our reactant? Do you see what I'm saying? That makes it a little bit harder because then I'm adding more steps. I have to place an alkene here in the terminal position. That makes it really hard, doesn't it?
Yes.
Yes. Yes. Thank you. So we know that it's not the carbon in green. Okay, it's not the carbon in green. It must be the carbon in red. So it must have been originally placed here in red. And so this small base still works. Small base with this alkyl halide makes the Zaitsev alkene. This still works. All right, cool. But how do I make this alkyl halide? And technically, I could just have gone from literally one, like there's only one more step to this. I could have just had one more step and I get to here. I'm working backwards. So I make an alkyl halide from an alkene. This is the alkene. What am I treating this alkene with? Whoops. What am I treating this alkene with to get to this alkyl halide?
HBr.
Okay, is it HBr and ROR or is it simply HBr?
HBr.
Yes. Because if it's HBr, guess what? We would have this alkene pick up a hydrogen, and originally you would have had a positive charge here, correct? Say yes. But then you would have a nice little hydride shift, which would leave this tertiary carbocation, where now, hold on, let me draw this a little bit better, where now this bromo anion could have attacked. And that gets us to our alkyl halide. So really, this is an easy synthesis question. And to recap, in organic chemistry 1, it's going to be a little hard to move in the forward reaction when you're trying to propose an efficient synthesis. What's easier is to work backwards. And we work backwards by identifying what our product is and what our reactant is. And our product, working backwards, how would we get closer to our reactant? We identify that this was a Zaitsev alkene, correct? And so we make alkenes out of alkyl halides. We could technically make alkenes from something along the lines of, you know, an E1 reaction with a hydroxyl group, but that makes it a little bit harder for us. So we're just going to say alkyl halides. Alkyl halides is an alkane with a good leaving group, or rather a halogen, because halogens are good leaving groups. Here's our halogen. We decided either we're going to place our halogen here or a halogen here. So either green or red. We picked red because if we were to pick the halogen placed on our carbon in green, that would move us further away from what our reactant looks like. And so we placed it in red because it makes our life a little bit more easier and it saves us steps. So we placed it in red, correct, here, and we identified the reagent. Since it's a Zaitsev alkene, we understand that we have to just place a small base like methoxide because that would make an alkene, a Zaitsev alkene. Okay, and how do we make alkyl halides? Well, we make alkyl halides from alkenes. There's different ways to make alkyl halides, but that's the most common way, especially since you've only covered up to chapter 8. You make alkyl halides from alkenes. So we have an alkene here. That was our reactant, but we needed to identify which reagents we would use. And it would either be HBr or HBr and ROR. If it was HBr and ROR, or HBr and peroxide, it would have technically added Br to the least substituted side, right? And since HBr with this alkene makes technically an E1 reaction, or rather a stepwise reaction, not an E1, an SN1, sorry, I misspoke. An SN1 reaction, which is stepwise, you end up adding a hydrogen to the terminal position, which creates a secondary carbocation. Luckily, there's something more stable than a secondary carbocation, which is a tertiary carbocation, and we get there by just doing a simple hydride shift. That hydride shift makes this tertiary carbocation, and now that Br that took away the electrons between H and Br, this Br anion attacks the tertiary carbocation position, and that's how we got our alkyl halide. Okay? Easy, done. The last final thing that Eric kind of wanted me to go over was basically the same thing that we've been talking about, is this anti-periplanar concept, because you're going to be asked something like this, and I just really feel that it's tricky if you don't practice, if you don't understand. And so I'm just going to do this final little question and explain, like, okay, why you might get one kind of alkene versus another. And the alkene in this question, well, usually, what do you guys know? Usually that what's more stable, a trans or a cis alkene? Trans. Okay. But here in this case, we're not going to get a trans alkene, and that should give you a huge hint. We're not going to get a trans alkene. We're going to get a cis alkene as our major product. And the reason for that is because this iodide, our halogen, our leaving group, and our hydrogen are cis to each other. They're not opposite to each other. And so I'm going to do, let me just redraw this because this is saying it's being treated with sodium and H2. This is just it's a base. And we're just probably, for E2 reactions, we're just going to give you terbutoxide, but think of this as terbutoxide. And so I'm going to redraw this, but on the other side, I'm basically going to flip this molecule. So I have something that looks like this. This would be CH3. Actually, let me just put this as methyl, ethyl. This would be ethyl and methyl, right? And I'm treating this with sodium amide. All right, sodium amide is an ionic species. It acts almost as an ionic species, which picks up a hydrogen. But we can't pick up this hydrogen as is, right? This is the symmetry, or not the symmetry. This is the anti-periplanar concept that I've been talking about. With all other questions that I've been asking in this recitation, I've basically just pulled from the opposite side. I've pulled from this side. Whoops. I've pulled from this side instead of this side because we couldn't rotate this cycle, right? You can't rotate cyclohexanes, but you can rotate, single bonds, sigma bonds, or single bonds. You can rotate these kind of bonds, right? So we would have to rotate this bond to make hydrogen anti-periplanar. So let's do that. This is a simple rotation of a single bond. So we rotate that. Let's imagine that we're rotating this single bond like this, where all we're moving is the back carbon. This back carbon, that's the only thing we're moving. And if we're moving that back carbon, essentially these substituents are going to be, you can bring your molecular modeling kit, you can visualize this in your head, you can just use like your hand. And if you see that, let's say this is your right hand, right? And I was to say for example, I don't know how this makes sense. If this was your pinky and methyl was considered your pointer finger, and this is your thumb, this is the back carbon, right? This is your right hand, and we're twisting it, just the back carbon, and we're twisting this. Think of your pinky now that was originally pointing away from you, like twist your hand. Now, this ethyl group is going to be pointing towards you. View your hand, look at your hand, rotate it, counterclockwise. Your pinky or this ethyl group is going to be pointing towards you. So let me just redraw this. Oops. Let me just redraw this. This ethyl group is now going to be pointing towards you. Okay. In this methyl group, if that was your index finger, where is this methyl group pointing towards? It's going to be pointing away from you, right? This stays the same. This is staying the same. And now this hydrogen is technically either, you can view this as opposite to each other, as anti-periplanar, or on the same plane. These things are pointing below and above the plane, below and above the plane. And hydrogen is basically opposite to iodide, but it's on the same plane. This is anti-periplanar. Anti-periplanar. Now that hydrogen is anti-periplanar, it can be picked up, right, by sodium amide, and the electrons shown in red being shared by that carbon and hydrogen are now being donated to form the alkene, kicking this iodide group out. Cool. So we know we're forming an alkene. And here's my question. And I alluded to this at the beginning. How am I drawing this alkene? Is this, so what groups are here? What groups are here? And what groups are here? What are the groups?
You have ethyls on top and methyls on the bottom.
Okay, and how did you get there?
Because they have the matching stereochemistry. I guess you could do the reverse as well. I just chose those.
Yeah, I mean, if you did the reverse, guess what? They're equal to each other. Because these are all sp2 hybridized, right? This is a flat molecule, right? These are all in the plane. And this is technically a cis alkene, which in theory, because two biggest groups are on the same side, in theory is less stable than a trans alkene. But because of our stereochemistry, originally, you had to twist this hydrogen. You had to twist this hydrogen by rotating that sigma bond to make it anti-periplanar to be able to undergo this E2 reaction, which would actually technically make the cis alkene. That's the only way of doing this. You don't get a trans alkene as your product. You only get a cis alkene as your product. And yeah, that's pretty much it, guys. I mean, this is all, this is what's going to be on your exam. Okay, I've covered every single thing pretty much that's going to be on your exam. Everything else is going to be easy stuff. This is just basically all the things that you need to show your work for, or visualize, or just imagine. I could keep going on with more mechanisms, more synthesis, more major product questions. But if you've viewed this recording, or if you've been here in recitation, then you should be fine. There's more practice exams. There's more practice at the end of the textbook. But unless anybody has any other questions, we are done for today. So real quick, how are we feeling? Are we good? Is everyone okay? Does anybody have any other questions?
I have a question.
Sure.
I get confused how do you know when you're doing the chirality? How do you know how to count, to know when something is R or S?
Chirality? Okay. Here. So RS is just clockwise or counterclockwise, right? Shit, let me share my screen again. Share screen. Okay, so I don't know, whatever we're talking about. Think of, I don't know, I'm trying to think of a good example that I've used previously or that I haven't used previously. How about, oh, here's a good question. Oh, I didn't even get to do this one. It doesn't matter. Let's think of anything really. Let's think of, actually, let's think of BR. Let's call this, I don't know, just a methyl group. We have an ethyl group here, and we have a hydrogen, right? We assign priority based on the highest molecular weight. So this is 1. This technically would be 2. This would be 3, and this would be 4. Correct? So we know that R, because we're going 1, 2, 3, and then 4. This is clockwise. This is R. Okay. And so, like, but let's say that hydrogen wasn't pointing away from us. Let's say same thing. Let's say that hydrogen was pointing towards us. This hydrogen is pointing towards us. Okay, now, again, assigning the same. 1, oh wait, this was an ethyl group. 1, 2, 3, 4. It looks as if it is R, right? But based on the Kohn-Ingold prelog system, we must understand that hydrogen, or our lowest substitute or our lowest priority group, I missed about priority actually. Our lowest priority group, whatever. Our lowest priority group has to be pointing away from us. And so if I did the swap method, this is 1, this is 2, this is 3, and this is 4. I'm basically switching whatever the lowest priority group is with the one that is pointing away from us, with the one that's pointing on wedge. And so I would switch 2 and 4, right? But if I switch 2 and 4, I have to then switch 1 and 3. Why? Because I have to conserve the original configuration. So this is 3 now, and this is 1. And if we view it this way, now this is, you see, this is counter clockwise. This would be S. And this is all summed up in your textbook. I forgot where exactly. Hold on. Oops. No, sorry, wrong notebook. This is all summed up in your textbook. Oh, where'd it go? Jesus. Okay. This is all summed up in your textbook. Where'd it go? Here we go. Tips for assigning configuration. This is on, I forgot what page it is. This is page 190 from chapter 5. Read rotating the molecule. This is the swap method. So if you swap something such that you have, originally you had like, I don't know, like whatever it was, you had to switch 3 and 4 in this case. If you see here, 4 is on the plane and 3 is pointing away. We had to switch the position of 3 and 4, but at the same time, we switched the position of 1 and 2 to conserve the same configuration. Okay?
Doesn't one have to stay on the wedge though, because it's the greatest priority?
No, it doesn't. No, it doesn't. It doesn't have to
Got it.
stay on. It just has to not be on. It can't be pointing away. The
Okay.
tip here, basically, you have to have the lowest priority pointing away from you.
Okay.
Okay?
Thank you.
Question.
Yes, go ahead.
So how do we know which way to draw the hydrogen to the left or to the right? How do we know?
It doesn't matter. It doesn't like dash doesn't mean left or right. It means pointing away. So it doesn't matter if you did this like the opposite way. It wouldn't matter. Like in this case, like so let's say we're doing this same example, but let's say okay, so we had Br, we had ethyl, we had hydrogen, and let's draw this such that I'm showing stereochemistry. So this is methyl, let's say methyl, right? I could have just as easily drawn this methyl, Br, hydrogen, and ethyl, right? And if I'm doing that little swap method in the first case, I get the same thing as drawn here, right? I get the same thing. So 1, 2, this was technically 4, and this was 3. So what's happening is I'm switching 3 and 4. But if I switch 3 and 4, I have to switch 1 and 2. Okay? So now I understand that this is R. But if I had this case up here, it's the same thing. So I have 1, 2, here's 4, and here's 3. I have to switch this such that we have 4 in 3's position, right? So 4, switch 3. This would be technically, what is this? Here was 1, now here's 1 here, and 2's here. Okay, so same thing. We got R in the first case. We're still getting R in this case. Do you see what I'm saying? So it doesn't matter where you draw the wedge, whether it's to like the left, whether it's drawn like this, or whether it's drawn like this. It gives you the same configuration. Does this make sense?
Yeah, thank you.
You're very welcome. Does anybody else have any other questions before we leave?
I have a
So
question.
just to make sure, like when you're numbering which way to do to assign configurations, it's the ones that have the highest molecular weight, right?
Yes.
Okay, thank you.
When we're doing electrophile and nucleophile centers, how do you know which one is electrophile and which one is nucleophile? Like for-
Electrophile.
Yeah.
Electrophile is the one with less electron density. Nucleophile is the one with more electron density. Let's see if I have an example of this. Conjugation. No, it doesn't matter. Okay, so here, real quick. So electrophile, okay, if I had something like this, for example. Okay, between this carbon and this atom here, what is the nucleophile and what is the electrophile?
Nucleophile is the OH, and electrophile is the carbon and the double bond.
Yes, and you can understand this because so this oxygen here is more slightly negative. It's a partial negative charge, and we can justify that because we can push this pi bond up, right? That pi bond can be pushed up, and if we push that pi bond up, we form a positive charge here. So that's how you would understand that it's the nucleophile. And also equally, or the electrophile rather. This is the electrophile, right? And equally, we could understand that this is the nucleophile because we could even, and this you will see in further examples, this could be pronated, this could pick up a proton somewhere and become a good leaving group. It could become water and then it could leave. And let's do that example. Since this is a hydroxyl group and technically it could be a good leaving group, if that left, we could internally attack here, right? But we're not going to show you those mechanisms or those cyclic reactions right now. But you could understand that this could equally have also attacked this electrophilic position. But anything with high electron density, and what I mean by high electron density is something with lone pairs or anions are nucleophiles. Okay, and I think there's a couple examples of this in chapter 7. I just don't know where I have it. I had some good examples on chapter 7 of like identifying good nucleophiles and good electrophiles, but there's a skill builder question in your book about this. How to identify good nucleophiles and good electrophiles. Just look at this table. This is on page 287 in your textbook. These are good nucleophiles, and anything that basically doesn't have a lone pair or a negative charge is an electrophile. They don't have a table of electrophiles, but you should understand what's an electrophile. Okay. So this table, nucleophiles. Okay. Anybody else have any other questions? No?
Just to confirm, bromine would be a nucleophile, right?
Bromine is a leaving group or a nucleophile. It just depends on the case. So like when we were doing those reactions, like it was like HBr, right? Bromine became a good nucleophile because it picked up the electrons between hydrogen and bromine. Do you see what I'm saying? We had like some kind of, we had some kind of alkene. This alkene acted as a good source of electron density, picking up that hydrogen, but it's not picking up that hydrogen necessarily. It's picking up a proton because the electrons here, or the electrons here between hydrogen and bromine, are now being donated to bromine. Bromine has originally, 7 electrons, And now that it picked up, technically this was its 7th electron, and it's just picking up one more. So now it has an overall negative charge. Once it has that negative charge, it can act as a good nucleophile and attach to this alkyl, this alkane. So bromine is equally a good leaving group, and the bromine anion is a good nucleophile.
Okay, thank you so much.
Okay. Anybody else?
How to convert the Fisher projection to the Newman formula? Like how to identify which carbon is which molecule located at the front carbon and the back.
You're saying Newman to Fisher?
No, Fisher to Newman.
Fisher to Newman? That's a little difficult, but we're not going to ask you a question like that. You know, like you would have to understand that like whatever this carbon is going to be the same carbon that's in front. So I mean it's arbitrary to say like which one it is. But let's say if this was like a methyl OH and a hydrogen, and this was a bromine, I don't know, an ethyl and a methyl. It's hard to say which one would be the front or back carbon because Newman projections depend on the way you're viewing them. But let's say if this was the front carbon and this was the back carbon, you could view it almost as, so the front of the Mercedes-Benz logo would have methyl, OH, and hydrogen. But who's to say what's on top and what's on bottom? Because this front carbon could easily be rotated such that now you have OH, methyl, and hydrogen. Or equally, you could have had, let's make more space. You could have had H on top, OH on the right, and methyl. And same goes for the back carbon. So this back carbon, let's say, would have, I don't know, ethyl to the right, methyl, methyl pointing to the, ethyl on the left, methyl pointing to the right, and Br pointing down. But I've easily could have twisted this or rotated the back carbon such that I would have ethyl to the right, methyl pointing down, and Br pointing to the left. Or again, I rotate it 60 degrees to the right a little bit more, just the back carbon, and I end up getting Br pointing to the right, ethyl pointing down, and methyl pointing to the left. And so there's a whole number of combinations that you don't know which one would be the correct Newman projection just based on, you know, because just like I did this Newman projection, I could have done this Newman projection, or I could have done this Newman projection. Same thing. Like this is just a rotation of the front or back carbons. Do you see what I'm saying? So there's not a specific way of drawing Fisher to Newman projection. What we're going to ask you is identify the stereochemistry in either the Newman or the Fisher projection and determine the relationship.
Would there be any
Got it,
questions
thank you.
to identify
You're
the
welcome.
relationship between a Fisher and a Newman?
No, we're not going to give you any of those. I think people would get too lost. So I don't think we're going to give you one of those questions. It's going to be like Newman to bond line structure, or comparing to cycloalkanes or cyclohexenes. Okay.
Okay. One more question about the exam. Do you know like how many estimated questions would there be, and like if there are multiple choices or mixed of everything?
They're gonna be, I don't know. It's probably gonna be like 20 something multiple choice and like 2 or 3 fill in the blanks.
And do we have to like do synthesis problem as like how you showed us, like the whole problem? Or
There's
just
gonna be one mechanism question and one synthesis question.
I have a question about the fill in the blanks. Do you mean like fill in the blanks
That
for
is-
like terms
that is-
or
Synthesis question.
I'm sorry, can you repeat that?
So the 2 fill in the blanks or the 2 like open-ended questions are the mechanism
Oh,
and
okay.
the okay.
All right, thank you.
All right, I'm gonna end the meeting.
Thank you.
thank you.
Everybody a good break and yeah, good luck. See you guys.